Hello, it's James from XRobots.co.uk. This is part one of a new project called Project Ultron. I briefly discussed this project in the last Hulkbuster video. And firstly, I wanted to say that basically Hulkbuster is still a main project and Ultron is going to be the other main project. I have got some other projects, including my 3D printed Star Wars R6 droid and possibly another BB8 coming up. But in fact, what we're going to see every other week is hopefully mostly either Hulkbuster or Ultron. So next week I'm going to be working on Hulkbuster and sawing up those ankles and putting the extra joints in and hopefully at least walking in them by the end of the episode. So that is still definitely a priority. After the legs are sorted, I'm going to be going back to the Hulkbuster helmet to make the mechanism that lifts it open. And that's going to be back into in-depth engineering, 3D printing gears, basically building my own giant servo to lift that faceplate up, including the electronics and coding that goes into it. So, do not fear, Hulkbuster's still going on, it's definitely going to get finished. The other bits of R6 I need to do are mostly cosmetic now, there's a few little mechanisms to go in, but the bulk of it is done, so that is going to be sidelined very slightly. Okay, so Project Ultron I discussed last time, and I showed some videos of some walking robots that I made a few years ago. I'd really like to make a walking robot, but I'd also like to make Ultron about maybe 30% bigger than human. So making walking legs is actually quite tricky and needs lots of power. I'd like to do legs as an aspect of it, but it might come as more of a proof of concept as part of the project. And I've actually got some plans to build things that work that I've really been thinking about for a while that I really want to do around the mechanics of the torso operating, and also some stuff to do with motion capture and the AI. So the priority for Ultron is to concentrate on those things, which I've thought out quite a lot. I'm going to tell you a bit about them in this episode, and then towards the end we're going to look at some actual motion capture stuff, which is a significant piece of this project. For the first part of this project, I imagine what Tony Stark would do. So in Age of Ultron, obviously he wants the AI basically to do good for humanity and make the world a better place. So the first part of this project is actually going to be making effectively a sort of brain controlled prosthetic. It's not really brain controlled. Well, actually it is, so let me explain. So let's just imagine I want to build a prosthetic right arm from the shoulder down. So I've got this black glove on just like Luke Skywalker, but imagine I've got a whole prosthetic arm and I want to control it. I could control it from my brain with a kind of hat you wear that measures brain waves, but those things are quite expensive. So I was thinking about whether there's an easier way to do it by working out what a prosthetic arm would do from the rest of my body language. So for instance, if I'm standing here and I want to pick up Ultron and I lean forward like this, then you can see that all my limbs are in a line. So my right hand is forward picking it up, my right leg is forward, my left leg is back, and my left arm is back as well. If I'm picking something really heavy up, typically I'm going to bend my knees and not my back and pick it up like this. So when my legs are both together, then my right arm will mirror my left arm pretty much. And if I'm standing here and I reach this way and I want this hand to help me pick it up, then pretty much my left leg is forward, my right leg is back, and my right hand will mirror my left hand like this instead of like this. So that's a simple motion capture study. Perhaps I also want head tracking so that I can fine-tune my right hand. So if I am doing this and then I want to move my right hand separately, I can use head tracking. I probably also want body tracking so that if I bend my body forward, my right hand stays in one position, so effectively subtracting that angle and it doesn't follow my body. So basically by tracking my body, my head, my left arm, upper and lower arm, and my legs, I can almost deduce what my right hand needs to do, and that's going to be the premise for this project. So I'm basically going to build a motion capture suit for the left hand side of my body and my right leg, and then try and sort out the logic to naturally control a right arm. And of course that would work for natural body motions as well, walking and all of those things. So that could be quite interesting. We're going to be looking at the motion capture technology in this episode. It's actually pretty simple, and I'm hoping to have that part of the project polished off within another 2 episodes. And that'll include building a little robot arm with RC servos, at least with an elbow and shoulder motion, so I can see if my prosthetic right arm would do what I'm expecting it to do. Then I'll be coming on to build it full size. But it's more than a prosthetic arm, it's a prosthetic body in the style of Ultron. So I'll be building Ultron's torso, head, and the right hand arm in the style of Ultron with 3D printing. So that means that Ultron will respond to the left side of my body. So if you can imagine in a social situation like a sci-fi convention, Ultron will react as I interact with people, only it will be doing it by working out what I'm doing on my left side rather than actually being puppeteered. Now I'm aware there's some other robotic torso projects out there, including the InMove project and various others. I'm not going to use those, mainly because I've got an idea for a design myself, but also people don't come to my YouTube channel to see me printing parts off Thingiverse. They like to see what I've come up with. So I've got quite a few innovative ideas, mainly reducing motor counts. So in most robotic torsos you'd expect to see 1 motor per degree of freedom. In your shoulder that's 3, so you move your shoulder backwards and forwards, in and out, and it also rotates. In fact, your shoulder blade floats so you can roll your shoulders. So to actually get human motion, you really need at least maybe 5 motors. I think I can do that with 1 and a clever series of clutches. So let's have a look at some example 3D prints. I've got several 3D printed parts on the table. The first one I'm going to start with is this one, which is printed in ABS, which is the same plastic Lego is made from. It's a rigid plastic. This part actually failed because there was a power cut, so normally you don't see inside the part. But as a result you can see it's not solid, it's got a low density infill in, so this is about 20 or 30% honeycomb. It's still really strong, and obviously about 3 times lighter than if it was solid, and it uses 3 times less material, and it's quicker to print as well. I've also got some NinjaFlex parts, which is a rubber-like material. It's a thermopolyurethane. So this is one of the drive belts from my R6 projects. In fact, one of the ones that actually drives the wheels. This stuff's incredibly tough. In fact, it doesn't snap until you elongate it by 900%. You could probably hang your whole weight on that. This one is actually solid. It's a really quite a firm rubber. There's also one called Semiflex, which is firmer still. Of course, if I do a lower density infill with NinjaFlex, I can make a softer part. So this one is about 30%, and you can see I can squash that quite easily. It's a tiny bit stretchier, and that's because of all the air inside squashing. So by varying the infill density of NinjaFlex, I can make a softer or firmer rubber-like part. Now, I've got dual extruders on my printer, so I've got some parts here printed in 2 materials. And in fact, with these 3, the white is ABS, which is rigid, and the red is NinjaFlex. So I've got a tyre there printed on a wheel, and this was printed in 1 piece with dual extruders. So the NinjaFlex is bonded to the ABS at the time of printing. I can put plastic, of course, the ABS, inside the rubber. So this one I've got a kind of track or a conveyor belt which bends easily this way. The red is NinjaFlex, but not the other way because of the white ABS pieces. And I can completely encapsulate the ABS inside. I've just left it here so you can see it. This is a really good example, which is a joint. So this could be used for prosthetics or robotics. Again, it could be completely encapsulated, but I've got rigid ABS inside the NinjaFlex. And again, if I use a lower density NinjaFlex, then I can make a more flexible joint. Or I can have a more flexible joint in certain regions by varying the infill density throughout the part. So I could have a joint, say, or multiple joints with different infill densities. And of course, if I vary the infill density of the ABS, then I can make a different type of property of the material there in terms of flexibility. So I could have a joint that's bendy here and even bendier on the next one that's all made in 1 piece. Similarly, the tyre could have treads which are softer on every tread or every 3rd tread by using a lower density infill. So there's a lot of things we can do here that are really interesting for robotics and prosthetics, not just drive belts, but lots of flexible joints, which will be good for my floating shoulder and all sorts of other aspects. We can also use this stuff to build cartilage between parts of the spine, if I'm going to build it in sections, and various other things. We can build compliant tendons and all sorts of things like bendy fingers made in 1 piece with rigid bones and bendy joints. So I'm going to use a lot of this in the project. My plan for actually driving the joints is NinjaFlex clutches, so maybe fewer large motors driving a NinjaFlex drum, and then having lots of little motors or servos disengaging clutches, so other drums which rotate and bind onto that drum, so basically a clutch that's servo controlled. So in a manual automobile, when you're driving and you're not pressing the clutch, the drive is engaged to the wheels and you don't require any force to actually convey that entire force of the engine to the driving wheels. When you press the clutch, which isn't very hard to do, it disengages it completely. So it's a very similar principle. And I'd have multiple clutches pulling multiple cables to activate multiple joints, all from one big high torque drive. So that's going to be the plan for most of it, the shoulder particularly, because it is so many degrees of motion, but also I could do all of the fingers in the hand and probably the wrist motion from one other motor. Now I could do all that from servos anyway, which I'm going to need for the clutches, but I could convey a much higher torque to each of those by using one big high torque motor and lots of really quite underpowered servos just to lift those clutches apart. I've offered quite a simplistic view there of essentially a robot arm that moves based on my body posture, based on some simple rules of like my leg position and arm position, and basically adding up and taking away numbers and applying those to robotic joints. In fact, if you're wearing a prosthetic that was controlled in that way, you'd probably find there's situations where it doesn't do quite what you want it to do. So I'm going to build another layer to this which goes in between the motion capture and the robot, and that's going to be the AI. Now in the movie Age of Ultron, the brain, when Tony Stark visualizes it, it's kind of floating in the air and it's all blue and swirly and you can see it thinking. So I'm going to do something like that. I'm going to build a 3D printed brain. It's going to be about this big, which is 1/2 meter in diameter, maybe slightly bigger, but it's going to be a very intricate 3D printed frame with lots of layers and lots of sections. Each section is going to have lots of blue LEDs, probably strings of neopixels, which are individually addressable for brightness and for colour in fact, so they don't have to just be blue. And I'm going to control it from multiple parallel processes, probably running on Arduino. Now I could write the AI on a laptop and write it in some other multitasking coding language, but it's quite good to actually be able to take the hardware and put it down and say, here it is, this is the actual brain thinking, and that's why I'm taking that approach. So your brain isn't really just a box where information goes in one end, gets processed and comes out the other end, and that makes you react and think and move. There are other things like reflexes and involuntary actions like your heart beating and breathing, of course, which happen anyway. And reflexes really take priority over anything else. Even if you're concentrating really hard to do something really detailed and important, someone comes and smashes a cymbal next to your head, it makes you jump, right? And then you screw up whatever you're doing. So what we really need is parallel processes, and some of those taking priorities over others. Now I'm building quite a social robot here, so it's going to be interacting with audiences and people who come to see me at exhibitions. It's probably going to be going to 3D print shows and things like that. So I need to build quite a social AI, and I've been thinking about this for several years and not actually getting round to it. My approach is going to be that the AI keeps track of its emotions in registers, and those will be of course reflected in the LEDs on its brain. So we'll have one that's how happy it is, one is how sad it is, how angry it is, whether it's hungry, whether it's irritated. It will have its own inputs like face tracking from cameras and also a microphone, so if it's really noisy for a long period it could get irritated. Of course I'll have manual override over those things with little plus and minus switches on the brain, so I can say, hey, you're getting a bit angry there, or I can feed it so it's not so hungry and irritable. And also it can also see you and decide what to do itself from those stimulus. So it can decide if it's jealous of your cosplay that you're standing there looking at it in and other things, and react to you however it wants to. So part of that is going to be through me, through the motion capture, reflecting my body language talking to you, at least my left side. Some of it will be its own senses, and some of it will be historic based on whatever it's thought in the past, and how those experiences currently relate to what's in its registers. And of course I'll be able to dump those machine state essentially off to a laptop and put it back again, so I can give it a kind of different history, or I can give it different emotions, or put it into a different state. So that's going to be the last aspect of the project, which is going to be quite a lot of coding, but also quite a lot of printing and a lot of visual stuff that's really interesting to look at and interesting for me to talk about. This is my BB8 droid, which I built a while ago, back in July. This is a 5-part series in my channel if you want to have a look. And I built this before we saw the real BB8 roll out on stage at Star Wars Celebration, so no one knew if it was just CGI, no one really imagined it was going to be a real thing. So the approach I took, not knowing anything about BB8 really other than the 3 seconds in the first trailer, is to actually build a robot that balances on the ball. So there's, I've got a robot here, the ball is effectively empty, and I've got omnidirectional wheels so it can drive in any direction. And the way it balances is by using an inertial measurement unit, which is this red board here with a black chip on it, which is an accelerometer, gyro and magnetometer, which essentially measures the angle. Now, to combine those sensors from the raw data is quite tricky, and I did quite a lot of code with quite a lot of maths in, involving doing filtering for each sensor, inverse trigonometry, and finally a PID loop to actually drive the wheels. And you can have a look at that code in my channel. The code you can also download for free if you want to go through it. So I need to capture 6 parts of my body, so I'm going to need 6 similar devices. The ones I'm going to use are a lot simpler and actually do some of that maths on board for me, so let's have a look at those. I'm going to be using the Adafruit Absolute Orientation Sensor, which is the BNO055, which I believe is a Bosch part. And Adafruit have mounted this on a breakout board and written an Arduino library and a really good tutorial. So you get a 9-axis of absolute orientation, which combine 3 axes of each accelerometer, gyro and magnetometer to just give you the angles. So basically it will give you the angle 100 times a second. So absolute orientation in vectors, quaternions, and basically just the angle, or you can get the raw data. So the default is the angle in degrees, which is actually quite useful, and various other things. So there's a full tutorial here using a thing called processing to dump serial data onto a PC application so you can make something move around on the screen. There's a full tutorial here, so we'll just quickly flick through the pages. So there's the chip. It tells you what the pinouts are. There's a soldering guide for mounting it, and also wiring it onto breadboard with an Arduino Uno. There's a library here, the BNO055 library, and also the Adafruit sensor library that you need to make this example work. And there's some example code here that basically connects to it and then dumps the X, Y and Z angles over a serial terminal. So we're going to basically power that up, get it wired up and see how that works. Here's my sensor wired up with an Arduino Uno. I've just got ground and 5 volts connected and also I2C. And I've got the example code loaded on already. The USB cable goes off to my laptop. This is the example code, so there's really not much to it. There's some stuff at the top bringing in the libraries and initializing the sensor. Then there's a couple of lines here that say get event, BNO get event, and that puts the data into some variables. Then there's some serial print lines here that print that data over the serial terminal, which we'll have a look at in a moment. So it's much simpler than what I had to do before. There's no complementary filters, there's no arctan, basically just gives me the answers. So this is going to make the motion capture suite pretty simple. So if I now open a serial monitor, we should see that it tests the sensor and gives me the X, Y and Z variables. So let me just zoom this out so you can still see it hopefully. And now if we move the sensor around, we should see all those numbers changing. So one of those on the left is for rotating, and the other 2 are for the other 2 axis. And this does a full 360. At some point it turns negative and then comes back at the 180 point, so I get plus minus 180, apart from the variable for rotating, which goes all the way from 0 to 360. So the plan is to use one of these sensors on each part of the left side of my body, and then I can get all of that data really easily. I need to measure 6 points of my body, so upper and lower left arm, body, head and both legs, and that's 6. So I've got 6 of these sensors altogether, 1 on the breadboard and another 5 here. I've also got this device here, which is another new Adafruit product, which is an I2C multiplexer, and that conveniently allows me to use 6 I2C devices with the same address with one Arduino, so I can basically give this a command and effectively it acts like a switch. So I give it a command for the first I2C port. When I read the data, it gives me the data from the first sensor, then I can switch to the second one and read the second one. So I probably won't get 100 Hertz out of this, which is the maximum speed for the sensor, but it will go as fast as I can scroll through them, reading them one by one. But it should be more than fast enough for this application to read all of those at once, all of the X, Y and Zs into separate variables. To make this whole thing wireless, I'm using a Bluetooth shield, which I've now installed on the Uno there. These are Maplin Bluetooth shields I got in the UK, and despite the 2-star review, I've actually found they work pretty well. If you look on the product page, there's a link to the manufacturer's website, and what you do is to configure them up to talk to each other, you put them on 2 Unos, and there's code for master and code for slave that you program onto each Arduino. You then put a switch in a particular position and open a serial console, type in 1 capital S, and put the switch back in the other position, and all being well, they should be set up as master and slave to automatically pair with each other, which seems to work. I did get an error on the master saying successful, then fail, but it works anyway, and they automatically pair within a few seconds of being powered on. That's what the red lights are. So now I have the master there is attached to the sensor, and in fact this USB cable just goes to a USB power bank. And the other one, which I've set up as slave, which will be attached to the brain of Ultron, is now plugged into my laptop. And of course the beauty of Bluetooth is that it exists on phones and things as well. So in the future I could write a phone app to replace the motion capture suit as a swap out option, which could still pair with Bluetooth. There are other types of wireless protocol like XB, but that doesn't exist on phones and tablets, and that's why I've gone for Bluetooth in this case. So we should see that in fact data is still getting spewed out from the other link there. So if I move this sensor around, there we go, which is of course totally wireless. So if I move this around, you can see all those numbers changing. That seems to work pretty well. What I've in fact done to the other Arduino is actually bridged out the Arduino, so I've just applied the reset to ground there, so the Arduino isn't even booting, and I've swapped over the pins, so these shields are jumperable for which pins you want TX and RX attached to for the serial link, so you can use software serial on any pins or UART serial on 0 and 1. And in fact I've reversed them so that the Arduino is not in use at all. All I'm using is the USB to serial interface on this board. So what we've got is a transparent serial link. So data is being read from the sensor over I2C. It's being read by the Arduino and chucked out of its UART serial that would normally go out of the USB. But instead it's going over Bluetooth to this one. And that is then just chucking that data straight up my USB cable through the USB to serial interface and into my laptop. And I've tested this up to probably more than 10 meters. They quote a 10-meter line of sight, but it works really well much further than that. So that means I can wander around with my motion capture suit and I'm not tethered to anything. So that is the end of this explanation and this episode. So next time I'm going to be taking all 6 of these sensors and the multiplexer and putting them in nice little 3D printed boxes and working out how to mount them all over me. And the Arduino that will probably fit on a belt strap with a battery, and then I'm going to multiplex all the data from all of them and shove it over the Bluetooth link and get that into variables at the other end. That is the plan for the next episode. So don't forget to subscribe to my channel and check back for more on this and on other projects.